Hi, I'm Marsha Pierce, the Director of Solutions Architecture here at Pure Storage, and with me today is
Anthony Nocentino, Principal Field Solution Architect here at Pure Storage.
And today we're going to talk about one of Anthony and I's favorite topics, which is architecting databases for performance. We both have been passionate about performance for a long time. And when I was a consultant and worked with enterprise customers, one of the things that I used to do was work on how databases were laid out on storage to get the most optimal performance that we could get.
Absolutely.
Right? It's a big hammer that affects everything. Mm-hmm. And so what I found really kind of interesting was that when DBAs do a lot of activities that they don't even really think about that are storage related. Mm-hmm. And so one of the things that we most commonly think about that maybe you don't realize is storage related is how you lay out your data files on your databases, right? We all know, and we're going to use kind of Windows as an example in this world, but it also applies to Linux databases, those that operate on a Linux operating system. But we all know that on the C drive, we usually put our operating system. Mm-hmm. We will put our data files, right, on the D drive. And we're going to create an L file, right, for our log drive. We usually have temp, and then we might put our backups on a different drive.
Mm-hmm. So what's the value of putting our database files across multiple drives like that, Marsha?
Well, there was kind of a couple things that we were trying to accomplish by doing this. Mm-hmm. One of them is that these different data files have different I/O profiles, okay, right? And so if you look at legacy architectures, both spinning disk and legacy RAID systems, mm-hmm, you only have so much throughput and like activity going through in queues for each one of these. So you're trying to separate out, you know, the very random nature of your data, sure, versus the very sequential nature of your logs.
Absolutely.
Going on. Mm-hmm. The other thing is that you're trying to get as many spindles behind all of this data as you possibly can.
Right, right.
Right? And we did things like we knew that we were going to probably mirror, right, or stripe our logs. Okay. We might do RAID 5 or RAID 10. Mirroring striping meant less protection, right, but more speed. And RAID 5 and 10 was more data protection. It was a little bit slower, but you were doing that to protect your main data source, right?
Right.
And so we would just kind of go along in this happily little world right here until like our data set started to grow.
Right. And so what we do when our data set would grow, Marsha?
We might take this file right here as it filled up, and we're going to cap it, right? Okay. And then we're going to create our E drive. And then as that fills up, we're going to cap that one. And then we're going to create an F drive, right?
Okay. So this is, as we add more data, we're going to add more volumes to support that data, and then more data files to stick our data into, right?
Right. I think this is what most DBAs tend to do, right?
So do you want to look at what that looks like physically inside of a disk subsystem now?
Yeah. Okay. Let's take a look at that.
So let's map that back to what that physically looks like inside of a traditional RAID architecture for platforms. And so these data files, as we would fill them up, as Marsha described, we'd add another data file, again, filling that up. And each one of these data files would be resident on some sort of disk subsystem. Again, this could be some sort of RAID supporting that workload, right? And so as we fill these up, and then let's go ahead and add one more to be our active data file. And so what we're looking at here, again, this would be the drives supporting that particular data file. As we ingest data or read data, we're really just getting the performance capacity of this individual disk or collection of disks to support the workload inside of that data file. Now, if I have tons and tons of spindles supporting this database, Marsha, does this seem like I'm going to optimally be using the disk subsystem in that particular database?
Absolutely not. And so that's what I made like, you know, a lot of my career doing was analyzing the performance of all of this different data. Okay. And I used to call it kind of, I would play Lund Tetris, right? I'm going to sit there and look and see how active is my orders table, how active is my customers table. And then what I would do was leverage different file groups, right? To put the data files into these different drives here so that all of them were active with different workloads so that they were all being used all the time and not creating these hotspots, right, with this one active thing. And I think most people are still doing this today.
Absolutely. So do you want to look at how this looks like inside a flash array?
Absolutely.
Okay, so let's go ahead and say we go ahead, provision a flash array to support this workload, right? And we migrate this exact database without changing its physical structures into flash arrays. So we get off of this storage here and we move this database into a flash array. Now, what's going to happen is the data files itself aren't going to physically change, but how the blocks are laid out inside of FlashArray are. So what we'll see here is that the blocks will be distributed across the entire array, not a subset of spindles or a subset of drives to support that workload. And so this particular database now, even though it's not physically laid out to take advantage of a traditional disk subsystem, inside a FlashArray, since we're distributing those blocks globally across the device, we'll get the performance capacity of this entire array to support this particular workload. Now, we worked with a customer recently, Marsha, that had this exact scenario. So what were some of the performance implications when we took them from a traditional RAID architecture into FlashArray?
Right, yeah, because they were running on direct attached NVMe drives, right?
Yep.
Which we historically would think was going to be like the fastest thing that you could do.
Right.
And so they weren't expecting much of a performance gain, but because they had not done this kind of architecture, how much more quickly did their month-end processing run?
Right. So this business critical month-end process, by just migrating the database from their traditional disk subsystem into FlashArray, was 40 times faster. Just this mission critical business process, to the point where they didn't believe that the actual procedure finished accurately. Then they checked their numbers, ran it again, and it was still 40x, right? They didn't have to change code. They didn't have to change the physical structures of the database, and they were able to take advantage of the FlashArray's performance capabilities and how it lays out its physical data.
And I think that's really interesting, right? Because this affects everything on your database. Every application is touching this, right?
Yes.
Everything's pointing to it. And if you could make everything run 40 times faster.
Right. If I was a developer, DBA, or even CIO, I'd be extremely happy with a no-code change for 40x performance gain.